Yeah. Okay, welcome. I won't say too much about that. Of course, you have a whole year now coming to these gatherings. But part of my hope, or part of our hope, is that you will indeed network. I mean, we can't declare from the top, you must network, but the idea is if you sit together for 4 weeks throughout the year, that you'll get to know each other. And the hope is that there really is some, there's some theorist over there who has some great idea that if you just sit, have beer with him for a few nights, then you'll find out about these things. Okay, so this is the QI League, and I was going to begin first by talking about the lecturers that you'll be hearing this week. Just we don't have to do this too much. This is all, it's rather schematic, so I wasn't going to say anything very extensive about each of them, just to maybe get their face into your mind. Oh, there's Barbara Terhall, whom you'll hear later today. And she will be lecturing on error correction. So I've thrown some icons up here. You should work this. So Barbara's a theorist, of course, and here's her idea of a qubit experiment. But you should probably try to understand what qubit experiment she has in mind. It's every line on here is a qubit, so you've got lots and lots of qubits. But part of the point is that once you have more than 2 or 5 qubits, there are increasingly complicated functionalities that they can achieve. And part of the big interest right now is, at how small a system can you start to achieve them. Okay, and I won't say anything more. You could say something about it if you wanted. Nothing.
No, I have my time.
Yes, you have your time. Now later today, actually we haven't seen him yet, but so we have a mix of lectures, mostly local, but we've called, the professoriate has also sort of conferred and said, well, it'd be nice if we have this as an opportunity to mix a little bit ourselves. So Renato Renner is arriving sometime later today. Helen, do you know what the arrival plans of Renner is?
Tomorrow.
Huh? I thought he was, oh, he's only lecturing tomorrow? Okay, sorry. I'd forgotten. Okay, maybe am I misinformed? Where's my piece of paper? What are the lectures today? I'm lecturing this.
Yes, you twice.
Sorry?
You are twice.
I'm twice.
And Renner and me. Yeah.
And Renner, yeah. So Renato should be arriving today. Okay, so we don't know, but he's a big guy. I mean, he's a grown-up. He can get here himself. Although it'll be challenging once he gets into the neighborhood how he'll get here. He'll probably call one of you. I don't know. Are any of you his student? I know he didn't have many master's students. Oh, maybe not. Okay, so there are no theoretical quantum info students from Delft. Okay, so he's lecturing on quantum thermodynamics, and this field begins with things that are kind of familiar. Okay, there's a battery, and there's a heat bath, and there's some quantum system in between, and there's sort of little machines for kind of thought experiments for thermodynamic cycles, but then there's a lot of math, and I don't know how he's going to mix it together, of how he will sort of bring it to you. But certainly his work has, over the years, had a lot to do with quantum cryptography, so there are points of contact with what could be done in the real world. The lecture, though, that's going to explicitly talk about cryptography, but also in connection with real information theory ideas, are those of Stephanie Wehner, who will be here starting tomorrow, I believe, or at least her lectures will start tomorrow. Actually, I note, if those of you who are looking at this might have noticed that there's one icon that hasn't changed here in the lower left, and that's because they actually do work together. So there's a little bit of this subject that they overlap in their technical work. And Stephanie does have interests in, these are all figures from papers that she's written, so there's, you will find very technical things. I mean, this is real GPS receiver, optical link, FPGA, CPU, but her contributions are mostly in the information theory side. So certainly the emphasis of this week will be theory. We've decided this being a sort of introductory week that we get sort of a basis of theory going, but not 100%. So Henrik Blum, who came in here briefly, but will be back here tomorrow, actually. I mean, we'll be lecturing here tomorrow. Will give the basics of solid-state qubits with an emphasis on the spin qubits. And well, I don't think I'll say much more about that. I mean, this is a set of icons. Here are the 2 qubits, right? This is more or less. Oh, maybe it's not quite the structure that you're thinking of, but I think you're thinking of a direct. Yeah, that's what I thought. Okay, so that's a familiar 4-electron device in the lab, and I think he'll explain that. But these are the basics of noise, which is extremely important. Isn't big, point of connection between theory and experiment. In fact, is the real understanding of noise and its meaning. Okay, I won't say much more about that. 1-electron device, 2-electron device. Details. I mean, many facts about material science if he chooses to go in that direction. But the construction in solid-state qubits, the actual physical construction of qubits is a very essential thing. So it's a whole important art of its own. Then later in the week, Fabian Hassler from here will talk about subjects that, well, in some sense, the big headlines go to Delft in this field. You might say that making Majorana. So I've thrown up some text here. There's Majorana, there's gamma equals gamma dagger, all these things that are becoming famous in the popular mind, even in the Netherlands. But we'll go at it in a more in a deeper way, hopefully. Fabian has actually worked with people in. Well, he worked at Leiden and he worked at Delft, or worked with people in Delft. So what are the subjects? Well, there's braiding of Majorana particles. There are nanowires, so they're again materials. There are particle hole symmetric spectra, and there are braiding. Exactly what he'll do with his lectures, I'm not 100% sure. So that's, but that's a few icons for your mind of Hassler. So that's the whole week, except for me. So now, what am I going to talk about? Well, I have. As I say, I have a few vignettes, is the way I like to say it. And I'm actually going to go to the blackboard shortly, just to play out a few of these vignettes. So I think I'm absolutely, ready to continue. We will. Let me just look at my watch. So, I had to transition from, host of Rector and logistics organizer to now actually lecturer. So I take a few breaths to get myself ready for that. I mean, in a normal lecture, I would put up an outline so you knew where I was going. But I thought I'd give it a slight bit of mystery. I mean, the mystery will be cleared up in a few slides, but at least the first few things I'll be doing this morning. I do emphasize, I think break times are very important, so this is a general rule of conferences, the breaks are too short. They announce coffee, and then the speakers go on a bit long, and then, the chairman is watching the time and said, well, go on another 5 minutes, and then in the end you have 10 minutes to run out for some coffee and then come back in. So I don't want that format. I'd rather have longer discussion times and a bit shorter on the lectures. So I'm reminding, of course, I'm saying these things to remind myself when is the time. Now I had a sheet which I've lost track of. What did we say? 10:30 is when I'm finished. Okay, I'm actually I'm planning on about an hour right now. So but let's see where we're going. So I begin again at the sort of icon level. But I wanted to single out a few things out of this picture, which, of course, which comes from an optics lab. I have to apologize to somebody out there in the world that I got this picture and I don't even remember from whom it is. But it's a relatively good guess that it's somebody who's working on experiments in quantum cryptography, and that it's a pretty serious effort. So what do I see here that sort of singles this out as serious? There's pretty close attention paid to the details of signal processing, which I think is good. I mean, quantum information is not just a subject in physics. You know, it's an information subject. So it's a subject of actually processing numbers of, and so I see here that these are Xilinx is the name of a company, and this is some particular device, a field programmable gate array that is processing information, I think processing key information in quantum cryptography. Pause for a moment. How many of you have had lectures, bachelor or master lectures, where you've gone through the basics of quantum cryptography? Right, okay, that was my assumption, that, and that goes along with my theme. I mean, essentially everybody. So this illustrates a few of my points, that number one, you've been sitting in lectures long enough, and you've heard all the basics, and so it's not my job or any of our jobs to go through the basics. So, so what I'm doing more in the lecture that I'm coming to is trying to pull out things, well, I'm going to try to illustrate ways of thinking and also tell you a few technical things that I bet you haven't heard, even though they are related to quantum cryptography, because there's a certain popular script. I mean, there's a lot of scripting, in fact, in lectures that people get the whole sort of scheme of how you explain Alice and Bob and the four states and transmit and reconcile and all that. And then other things that are almost as interesting get neglected. So, but let me proceed on in the way that, so this is somebody who's doing a very serious experiment in the infrared. I think part of the point of this is how to do cryptography at really technologically interesting frequencies. So whenever you see 1550, that means you know, the sort of the prime band for telecommunication, infrared band for telecommunications. Are these guys? Oh, you're just filling in your sheet. I was half expecting that somebody would go onto their pad and try to find this chart. That's not necessary, by the way. So there is a quantum channel. So there's a place where there are photons passing through fiber. There are wavelength division multiplexers. There's other stuff about organizing information. Where else did I want to mention? There's a separate use of FPGAs here. There are avalanche photodiodes, so there are quantum measurements in various places here, APDs. So there are things that measure single photons. For some reason, which I don't understand, there are both indium gallium arsenide APDs, photodiodes, and somewhere over here, I notice there are silicon photodiodes. Now I'm not seeing it. Is it further over? Let's see. Up, up, up. Left, left, left. Down, down, down. Ah, yeah, silicon APDs. Okay, thank you, right. This is somehow part of the state preparation part. Anyway, finally here, I mean, after you stare at this for a long time, you finally notice BB84, and I think those, maybe you know that's the acronym for the basic sort of theoretical protocol that's being enacted, the Bennett-Brassard protocol involving 4 quantum states. And I'd usually stand here and, okay, polarization vector this way, polarization vector this way, polarization vector this way, and this way. So those 4 choices are what Brassard and Bennett introduced in 1984, you know, and built a whole scheme around, and that's what's being implemented in this experiment. And I'm sure this is somebody's PhD whole life. I mean, well, their whole PhD career is this, you know, making this work. But I'm not going to explore any further the real guts of this experiment because I want to more have fun. So this is somewhat my theme that, I mean, you guys don't have the privilege of knowing Charlie Bennett. the B of the BB84, which B? Brassard, Bennett, first B, so they always did alphabetical. But he had always an emphasis, I mean, he's still alive, he's still thinking about things. His emphasis was always on sort of playing, essentially. And I think it was, well, you might say kind of accident that BB84 has become a big sort of technical thing that people devote whole experimental PhD studies to. I mean, I think it's an accident and it's not, because he was playful but very focused on things that would be new, that would really result in new ideas. So this was sort of fun with Alice and Bob. And so I'm going to introduce as my first technical subject another twist on not even quite cryptography, although in the end it finally gets to cryptography. But it's a game in some sense, and it's the so-called UPB game. Okay, another show of hands. Anybody know what I mean when I say UPB? Nobody at all. Fantastic. Okay. So, so this is the kind of thing that you could easily have had as a lecture subject, but it just didn't come up. Lectures are too full already with lots and lots of things. And you may say, well, why do I have to learn one more thing? And well, it's because you're sitting here and you should learn something. But you should learn that there are things out there in the literature that you have to find yourself, because when you start working on some problem, maybe it's an experimental problem, you say, has there been any theory relevant to this? And I didn't hear anything about that in any of my lectures. That shouldn't stop you. And indeed you have to start looking, because maybe somewhere out there somebody has thought about this. Now, this is a strange enough thing that, I'm not going to yet reveal what UPB means, although you'll see it in a couple of slides. But you'll see it as part of the explanation of the game. Now, this actually happens to be work that I did with Charlie and also with Barbara, and it's getting to be 10 years ago or so it's not actually new stuff, and there were various other authors involved. Okay, so, oh, sorry, that's already off. I'm reminding myself that actually now I'm going to the blackboard. I have to find my notes. So the game is a state measurement game. So I want to make sure I get set up properly first here, because I want you to be able to see the blackboard. Let's see, if I keep the blackboard here, maybe some of you, any of you going to have trouble because of this little table here, seeing what's on the blackboard? No, okay. So this is a setting where there is an Alice and a Bob, and they're told that their job is to measure something, and so there's sort of a third party, sometimes called Charlie, who decides they're going to present Alice and Bob with a state, with a quantum state, and they have to measure it. And so one version of this game, let's do first a fairly hard version of this game, or apparently hard. Suppose that this referee or Charlie or whatever declares ahead of time that the rules of the game are that he will offer them one of these two states, but he won't tell them, won't tell Alice and Bob which one it is. And the point is for them to figure out which. So these are Bell states. So these are entangled states. And basically the job of Alice and Bob is to get at this plus, or whether this sign is plus or minus. So I wonder if any of you know about this, although I doubt it, actually. I mean, has this come up? Have you ever been had this question posed to you? This is not yet the UPB game, by the way. This is a sort of a warm-up to the UPB game. Can Alice and Bob actually Sorry, I have to first explain what the rules are of Alice and Bob, that they are given these particles. So there's, say, particle 1 or particle A and particle B. This is a two-particle state. Alice and Bob are given these. So they're given them by some, external force. Some Charlie has come and presented them or plopped them down in the lab. But after that, they are not allowed, they're not given a quantum channel. So no Q channel. But they can communicate. So there's this Ethernet. So no channel, but there is the Ethernet, or the classical channel, or the telephone, or whatever. And they both have well-functioning quantum labs, so they can make measurements on their particles, and they can maybe perform operations, the usual kind of quantum gate operations on their particles. So at the end of some protocol, would it be possible for them to identify 1 versus 2? In other words, state 1, can they report back to Charlie, yes, we had state 1, or yes, we had state 2? This setting, by the way, is what's called LOCC, this stands for local operations and classical communication. Has anyone heard of LOCC before? Yes, okay, so this is in the curriculum, not only at several universities, I notice. So this is so part of what we'll be talking about are LOCC type games, things you can do with LOCC. Now, I don't want to make any big deal out of this particular warm-up game, but okay, we'll do it as a vote again. How many people think that Alice and Bob can make this measurement and report successfully whether it's 1 or 2?
They can make single-shot measurements, right?
They can make what?
Single-shot measurements.
Yeah, okay, that's what I mean by well-functioning lab. They've already got the, they've got their good, superconducting qubit lab or good optics lab, the APDs or something. Yes, they can definitely make single-shot measurements is the premise. Okay, so think yes. Some people no. Okay, not sure. Let's do not sure. Yay, okay, that's great. Okay. I mean, let's do a few things. You may say, well, the information here is a bit hidden, you have to admit. I mean, this is a classical bit of information. Now, recall your rules. These are orthogonal states, right? So they are taking the whole world together. In other words, taking this as, or not worrying about locality considerations. These are orthogonal, right? What do I mean by that? I mean, of course, that the inner product of psi 1 and psi 2 is 0. So von Neumann says we should be able to measure them. But the trouble is that this is a very non-local kind of projector, you might say. And what can Alice and Bob do? Well, they could measure. Alice measures 0 and Bob measures, Alice does a 0-1 measurement, say, and Bob does a 0-1 measurement. And what have they learned? Nothing. I mean, they can communicate all they want, but in fact, these two states are indistinguishable from that point of view. So they would have to do something. If they're going to succeed, they have to do something more. Now, in fact, they can succeed, and it's actually not such a hard job. Let's see, I didn't actually work it out, what would be the thing that they need to do. I mean, I know the general rule, but I didn't work it out for this case. But it's something like the following, that there are, well, it's well known that if Alice and Bob can perform simple quantum gates, namely just Pauli operations, X, Y, Z, in other words, Pauli 1-qubit gates. That they can turn these into other Bell states. So for example, if I had if I manage to turn one of these into a Bell state which looks like this, if I turn it into a singlet, for example, and suppose now the job is to distinguish 1 from 3. That's easy, right? Because Alice and Bob make their measurement. If it's state 1, the 2 bits agree, which they will find out by doing this Ethernet communication. And and therefore they know it's 1. If it's 3, the 2 qubits will disagree, or the 2 measurements will disagree. So then with the communication step, they'll be finished. So that's a sort of non-obvious example. It turns out that Alice and Bob, any pair of distinguishable states, whether they're entangled or partially entangled or whatever, are actually always distinguishable by such a game. Okay, now we'll do something which sounds, now we will finally get to UPBs, and we'll do something that sounds even more trivial, or is at the outset a lot more trivial. Suppose that the states to be distinguished the ones that Charlie offers are this list. I may not draw all of these, but let me stop at some point. Okay, that's a list of states. Now again, this is Alice and this is Bob. And these are just product states. Oh, I've slipped in this. Well, it'll become important. I'm actually going to 3-level systems for part of this discussion, but that's not, hopefully not a big deal. I could have left that out for the time being. Charlie produces these states out from this list and provides them to Alice and Bob. In other words, separates the particles. Alice gets one particle, Bob gets the other. So now the list is psi1 is this, psi2 is that, psi3 is that, etc. So 5 states, let's say. Now, this is not such a hard job. Is everyone comfortable with the idea that, yes, there's clearly no difficulty for Alice and Bob to distinguish among these states? Because they are all, there's no entanglement involved. They're just product states. Oh, I said the title of this was UPB. The P is product. So this is a game that only concerns product states, only states without entanglement. So we agree that if the game is set up this way, it's a trivial one for Alice and Bob. They measure in the usual way. They measure whether they have a 0 or 1 or maybe a 2. They communicate back and forth. After one round, they know, Alice had a 0, Bob had a 2. That was state 3. And they will successfully report that to Charlie, to the referee. So you might be tempted to say, well, there's nothing to this. We'll make it as a sort of theorem. And then we'll work on proving it, that joint measurement, LOCC measurement, this still took some communication, of course. That is, Alice measured 0, say, but she has to wait to hear from Bob whether he got a 0 or a 1 or a 2 before they both know. Alice also sends her information. Before they both know that which of these states it was. Of course, in this case, they could have reported their knowledge directly to the referee. Alice's knowledge of 0 was enough in total for this. Okay, but the theorem I'm going to explore is that joint LOCC measurement in any product basis so here's a product basis. Can be done. Can be done successfully. In other words, that after some measurements and communication that Alice and Bob have in fact identified the product state. And the proof is, well, the beginning of the proof is very simple. The proof is this is false, so there's no proof. So now this may sound paradoxical. That's in fact the whole point, that it should sound paradoxical because I've made it sound like a trivial thing. I haven't quite said what I mean by a product basis, so that's where I have to go on and explain the sort of non-trivial aspect of this little game. And then we'll finally learn what the U and the B means. Oh, actually, B means basis, so that's not anything strange. We just have to get to the U. So here I come to this sort of game that we made up and turned out to be more interesting than you might have thought. So I've already mentioned that I'm going to work with the so-called trits. Well, Q-trits, sorry. So I'll work with three-level systems because it turns out this puzzle is way more interesting for three-level systems than for two-level systems. I'm toying with the idea of there being a homework somewhere in here. So those of you who are eagerly anticipating the credit point homeworks, you could imagine already certain little problems that come up here. Okay, so I've just drawn this little board in order to depict certain things, to sort of give a pictorial idea of some states. So of course, it better be something more complicated than this, because there was nothing to this. Nothing hard about this game, and it was clear that if I write more of these states, I have 9 of them potentially, but if I write all 9 of these states and I say, can Alice and Bob do this LOCC measurement game, of course the answer is that they can. But it's surprising how easy it is to break that with just some simple observation. So I want to actually use a state like the following, that it's a 0 for Alice. I'll use a slightly expanded notation for a moment. And I'll use a different basis state, but this is where the sort of connection with Bennett-Brassard comes in. So this is Bob. So that's a product state, right? And it's the beginning. I can make a product basis that has that as one representative. Let me make as a sort of cartoon what that state is here. It sits in both of these boxes, so to speak. And I'll make a little blob, and I'll put a plus here. And that's just a little notation that I make up special purpose for stating, for having something in my mind for what this state is. I can also, of course, have a minus, so I'll have a plus and a minus. Now, let's start making a basis. Let's start filling this out with orthogonal states and see what we can come up with. Well, there are various things. I'll go right to the interesting one. So let's pick these two also. I could stop and already ask the LOCC game for this, but I'll go a little bit further, although there's already a little bit of interest in that. But notice I put this over here rather than there. These two, now these are 4 states. Just to write this out one more time in regular notation, this is a 2-state for Alice, and now it's 1 plus 2. Good, so that's, this just saves me writing a line of algebra to make little cartoons like this. So these 4 states are actually still distinguishable, but there's still a little trouble, though. Alice and Bob couldn't quite have acted independently, you might notice. That so here's a protocol that works for these 4 states, which is Alice measures in the normal way. That is, Alice does a normal 3-state measurement. And she reports the outcome to Bob. So I'll begin making a few colors here. So when she makes her measurement and sends the outcome to Bob, Bob has learned this information. So he's gotten that information. He better, well, if she got a 1, it means there's some problem, like Charlie lied. Because there was, you know, there has to be an agreement ahead of time of which states are involved in this game. So Alice detecting a 1 would be either the measurement fidelity isn't high enough, or Bob or Charlie didn't set up the game properly. So she should have only gotten 0 or 2 in this setup. And then if Bob hears 0, then he knows it's one of these two states. So he just has to set up a distinguishing measurement that will distinguish 0 plus 1 from 0 minus 1. So of course what that means, let's draw a block sphere. You know, 0's here, 1 is here. Let's see, depends on my coordinate system, but 0 plus 1 is here and 0 minus 1 is here. Well, most of you know you do various ways of thinking about it. Fundamentally, you're allowed to make such a measurement. If you want to think more, how do you do it in the laboratory, you need to do a rotation, you know, some appropriate pi/2 rotation so that it's along the 0, 1 axis, and then you measure 0, 1. So Bob can finish with these two states, but if he got a 2, if he heard from Alice that her outcome was 2, he has to do something different. He has to do, well, it's not a block sphere anymore because it involves the third level, but he has to do that, a different rotation, you know, the rotation that involves rotating between 1 and 2. You know, that's another block sphere, you might say, but it's a different 1 qubit manipulation. And then he can measure. So then that's finished. But now from the way I've drawn this cartoon, you can maybe see where the problem lies. That is, how do I finish this? This is like, you know, playing some kind of strange domino game. I'm covering, you know, I want to make more states. I have to have them orthogonal to these. But in this sort of tiling game, you can just put more blobs like this. And now this is now a complete basis, right? It's 9 states, and I've thrown, there's this one left over, that is that I can't cover a 3x3 board with dominoes, so there's got to be 1 square left over, but that can be just its own state, 1, 1, and that's orthogonal to all the others, and these are all mutually orthogonal, and so this is a product basis. But it's not, well, it's not your usual product basis. And in fact, this is an example for which the theorem is false. There is no strategy for Alice and Bob to perform, you know, Alice tries some measurement, reports the data to Bob, Bob does some measurement. You could ask, what about multiple rounds? What if they try probing only weakly? So the proof that this is false, I had some note about it. Oh, it takes about 10 pages. This is a hard, okay, this is where if you want to make a nice story out of this use, you don't proceed because this is to technically prove that this is not possible. Well, I should say in our work it was really long. There were subsequent papers that I think would get it down to 2 or 3 pages. I don't know if that was ever systematically done, but there were people who noticed that there were better mathematical approaches to this proof. But it's a hard thing to prove in general because, you know, well, you can easily disprove any particular strategy, and maybe I'll go through that. But actually to prove that there's nothing whatsoever that Alice and Bob can do within this LOCC category, which includes, as I said, measuring, for example, weakly, you know, getting a POVM outcome of some kind and reporting to Bob, and they could have many, many rounds. I'll in fact illustrate how close this is to being true by just erasing one state. So let's, so as you see, there are many, many variants of this. So let's try 8 of the 9 states. Let me erase this. So we're going to do the 8 out of 9. And the question is, well, I will say that it is in fact true that you can distinguish 8 of these 9, if that is, if the game is just the same, except that Charlie promises he'll give one of these 8 states, but he'll never give the minus state here. So I'm just curious, well, this is sort of a matter of how you feel about this. So in looking at this, I doubt that any of you have scribbled down the answer, but you feel like you know that the answer that is really true, or you're not sure, or you're waiting to hear from me. Okay, you're kind of waiting. It is Monday morning, after all. Okay, so what's the game here? Or how do I proceed is what I should say. First of all, I'm going to prove that this is measurable by just constructing, by going through an LOCC protocol that succeeds in doing this. Now, the first observation is this. Doing this red strategy, that is Alice measuring everything, would be very bad. Why would it be bad? Well, it's because the distinguishability of these 2 states is not in its 1-2 content. It's in this whether there's a superposition 1 plus 2 or 1 minus 2. So this must not be done. Now, experimentalists should wake up at this point. Well, I haven't noticed anybody sleeping yet, but I actually like to make this as a particular point, that when these games are being developed, and this is pure theory sandbox, you come to a point where you say, oh, I want to have a measurement for this purpose, but this is not the only purpose that you'll hear about for which you'll hear such measurements. I want a measurement that distinguishes 0 and distinguishes 0 from 1 or 2, but does not distinguish 1 and 2. So that's a clear theoretical idea of this sort of partial measurement. And I can assure you there are many uses for such measurements. The theory is in fact filled with, quantum information theory is filled with interesting protocols that rely on things like this, and more complicated. But this is sort of the most easy version of saying I'd like a measurement that is incomplete in the sense that it gives no information about whether 1 or 2 was present, but is single shot from the other perspective. That is, will in one shot distinguish 0 from the group 1, 2. So that's an interesting story of its own. How do you do that? How do you do that for a quantum dot with 3 levels? Or how do you do that with a superconducting qubit with 3 levels, a transmon? Actually, that would be a very practical question to ask for a transmon. We do kind of know how to do such things, but I would not claim that we've found the most optimal way of doing such a thing. So, okay, but let's return to the sandbox, to the theory idea. So Alice will begin with this red measurement. So let me make a little tape or a little tree here, in fact. So there's an Alice measurement, and she will get 0 or 1, 2. So this is how you report it. I say I've got 1 or 2, but I've been very careful not to figure out which one. Now she communicates. So this is the Ethernet. This bit of information gets sent to Bob. Now Bob does something different in the 2 cases. If Bob hears that it's a 0, then he knows he's working up here. And he has to, he will do this. He will do 0, 1, or 2. That is, he'll construct that measurement, which, if I go for more colors, I could say he sees it's harmless to do this. you might say you've already done some damage to this state, but it doesn't matter, actually, because it won't. This state has been projected, this 0 plus 1 state has been projected to 0, but it doesn't hurt the fact that it's, eventually they will be able to agree that that was the state, even though it's been, quote, damaged in the process of projection. Okay, so Bob now does this, this measurement, but the job is not done because now, well, here it's done. In fact, this is a case where they know that this state, I haven't given these numbers, but the state that was sitting here originally has been successfully identified. In the case of 0, 1, the job is not quite finished. Bob has to transmit again back to Alice, and then she does, I'll call it a plus-minus measurement. That is, there's a job, final job done to distinguish which of these two states it was. And so with a measurement 0 plus 1 versus 0 minus 1, remember the block sphere and rotating back and doing that kind of measurement. So then that branch is done. This illustrates some things about LOCC games. They're often not of fixed depth. That is, sometimes there's some branches that go shorter, some branches that go longer. These go a little bit longer even still. So let's see what happens on this side. So Alice reports that the state's somewhere down here in this diagram. Now, Bob considers what can be done safely, and he notes that this can be done safely. That's why this diagram with little dominoes is helpful. You just by eye see, are you cutting through a domino or not, basically, in this sub-region of this tiling. So Bob will now do a 0 versus 1, 2 measurement. So notice different, not the same as the measurement that he did in the other branch. So he had to wait. He definitely had to wait for Alice's information in order to do this. Now let's see. If he gets 0, then it's almost finished. It's been isolated to this domino, so to speak. And just with sending this back to Alice, and Alice again does a plus-minus measurement, the appropriate plus-minus measurement here. Let's see, am I saying this right? Let's see, this was Bob. Bob measured 0. Now Alice measures that, yes. The thing I'm worried about is this one. Did I say something wrong here? Oh, sorry, I said something wrong here. That this was not Alice's job. This was just more work by Bob. That is, we were looking at this state. So forgive me, I erred. But this is not unprecedented. So Bob actually has this state in his possession. That is, he can safely now measure plus minus himself on this state. So that was this case. However, in this case, it really was a job for Alice to distinguish this pair of states. Now we're still not done because, okay, now I try to keep things straight here. Bob has, okay, Bob has done a measurement and it's been narrowed down to this region. Now Alice had better try this measurement. So Alice will do that measurement and get either a 1 or a 2. So she distinguishes, yes, so Alice distinguishes whether it's a 1 or a 2. Let's see, in the case she got a 1, then it's done. Because then if you go through this whole chain, then that's been uniquely identified as the center square. No, sorry. Let's see, is that true? No, still getting that wrong. If she gets a 1, she's in this, and she still has the job of measuring, or they have the job of distinguishing these two, which takes another round back to Bob, and he measures 1 versus 2. In the case that it's down here, then Bob, it also has to go to Bob, and he does a plus minus. Sorry, as I said, I was not flawless in that. I think the final chart except it's not erased so well. This is actually a correct final chart. But I hope you get the idea. I mean, I could also give this as a homework, that you say, well, clean up Professor DiVincenzo's mess on the board. And I'm sure you could do it. But it relied on the fact that there was only one of the two possible states here. If I had allowed the minus state here, then this protocol would not have distinguished those states. It turns out for all 9 states, there are protocols that do a better job than this of sort of partially distinguishing, getting partial information about which state it was. Yes?
When does it break down again?
You mean when does this, when do you fail to be able to, when would it break down if you do this, if you had this minus state? Yeah, it would break down right away because, let's see, because I said Alice's strategy was to measure this 0 versus 1, 2. But at that point, if she's applied this projector to one of these states, they become forever more indistinguishable to Alice and Bob. They've lost their chance to distinguish them. If Alice has already learned that it's 0, and Bob, checks that it's 2, that's all the further information they can learn. They've just damaged the state by projection, by the choice of projector that they have made. Okay, now this, so this is an interesting game. We actually called this non-locality without entanglement.
Excuse me?
Yeah.
This protocol, can we choose any 8 states, and there is a protocol for distinguishing them?
Oh, very good question. Any 8 except for the middle one. If you leave out the middle one, it's still not doable. Let me think about that for a moment. Yes, I think that's correct. But that gets me to my next topic, in fact. Great lead-in question. I mean, you can start looking for the sort of the whole catalog of which subsets of these states are not measurable. But in fact, I think those are the only cases. The middle state is special. But otherwise, and if you leave out only one of the perimeter states, then it makes it measurable. Was there another question? Yes.
So I understand the main point is that we cannot draw a straight line that doesn't cut through a plus minus.
Well, that's not, unfortunately, that's not enough. That gives you an idea that it's hard, that at least you can't see any way of making the measurement. To actually prove that it's not possible to make the measurement takes really harder work than I'm going to do here. Yeah.
Because we do 2 measurements for same qubit, so the 2 measurements should be commutable. Otherwise, the measurement is.
In this protocol, you never encounter a case where you do a measurement on the same Hilbert space as before that is incompatible with the previous measurement. And yes, you can use the word commuting, but you have to be careful that it's conditional upon where in this tree you are. That is, I mean, there are measurements that I've just stated that are not compatible with each other, but they are, in any particular sequence, they are not both done. In other words, you have, let's see if I have an example here. Yeah, you have here right, I mean, there's at some point, for example, Bob does this plus-minus measurement, and in other parts of the protocol, he does a regular 0-1 measurement. So those are definitely incompatible measurements. They are non-commuting measurements.
Okay.
However, because of the way the protocol is structured, he does either one or the other based upon the information that he's gotten from Alice. So that's how this, those can be non-commuting, and yet they do not damage the state because they've been done in a careful sequence.
Okay, can we still distinguish the plus state or minus state after we got the 1 or 0 for Bob in the first situation?
I have to understand which one we're talking about.
Alice got 0 and Bob got 0 or 1.
Okay, yeah, that would be a bad protocol, indeed, and that would be they will have failed in the protocol. That is, they will not distinguish. They will not be able to distinguish plus and minus in that case.
the plus minus behind the 0, 1 is not possible to be done.
Well, here you mean, or?
Yeah.
Well, I tried to illustrate that for this particular set of states, well, without the minus, then everything does work because you never, Bob is never forced to do a measurement which will damage the states that he knows he has. And at the outset, they don't know which of the 8 states they have. But after Alice has done a measurement and reported to Bob, there are only, let's say the 0 state, there are only 3 possible states that it could still be. They've already ruled out 5 of the 8 states in the first measurement. And so they don't have to worry about any measurement that would do damage to these states is not a problem, because you know already that those states are not the answer to the puzzle, or not the state that Charlie gave.
So the measurement Bob does has only 1 step instead of 2 steps.
Well, oh yeah, sorry. Okay, this was misleading. I mean, I could have indeed done the job. Let me change this one more time. Once Alice has said 0, then Bob in 1 step can do this measurement, which I'll state a little more cleanly. 0 plus 1, 0 minus 1. Well, it's not at all cleanly because of the state of the board. So if Bob does that 3 outcome measurement at that stage, the job is done.
So 1 step.
So in that case, 1 step, yes. I mean, again, it's somewhat of a practical question whether someone in the lab could actually do that as a 1-step measurement. I mean, he may have to at least do some quantum gate first, and then do some resolving 3-outcome one-shot measurement. You look a little puzzled, but I mean, we can talk. I promised a big long break, so in 15 minutes we'll be, or so, we'll be heading off to a break. So, okay, but now I wanted to come back to the question, you know, what's more to this game? This sounds like, well, okay, there's something true that maybe we didn't know before. This doesn't happen, this happens first for 3x3 layouts, it turns out. So it's false for, there are many examples from 3x3, but 2 times 3, in other words, a qubit and a qtrit, it is true. So there's this product basis game always is solvable as an LOCC measurement procedure in 2 times 3. Okay, but I'm going to show you one other thing that then we went on to do. Again, it was sort of along the lines of asking, well, how many other states can we make up, or are there any other interesting states among this, you know, in this sort of class of problems? So here's the next game. So I'm going to stick with this sort of 3x3 layout. So this is sort of the next story. And I put down my 4 blobs, but let's say I only put down the minus states. Now those are 4 states. Now there's another kind of interesting state that's another product state that is orthogonal to these, and it's the following. Let me make enough space for it. So the 5th state in this game, I'm going to use it. Let me not say 5 because I have some funny numbering coming up. So anyway, there's another state which is the following: 1 over the square root of 3, 0 plus 1 plus 2. That's Alice. And then the same thing on the Bob side. I shouldn't fly off the end here. 1 over the square root of 3, 0 plus 1 plus 2. Bob. Okay. So what is that? I mean, why is it orthogonal, first of all? Is anyone puzzled about that? You know, let's check. So this is supposedly orthogonal to, let's say, 0 plus 1, no, sorry, 0 minus 1, that's actually the whole point, times, which one do we have? Let's see, that's going to be this state. So that's 2 for Bob. So we're going to do a check. Is this really orthogonal to that? And of course, it's not at all orthogonal on the Bob side, if you look only at the Bob state, but it is orthogonal on the Alice side, just because of the minus being changed to plus. It doesn't matter what's left over in the 2 state. But because of by choosing this very symmetrical state, it's therefore orthogonal to all these. So it somehow sits on top of all of them. Well, there's no good tile representation for it. In our work, this is called the stopper state, and I'll explain that in a moment. Well, maybe I'll say it actually, yeah, I'll come back to this. It actually has to do with baseball, but maybe I'll come back to that story. I think there are no Americans in the audience, but there may be some baseball fans. I don't know. But you have to watch it with these papers we wrote at IBM that has a lot of American sort of culture mixed in funny ways. Anyway, so that's a 5th state. So I have 1, 2, 3, 4, and now I have 5. I could already ask this LOCC game, but I'll pause on that for a moment. But I'll ask, well, okay, that's 5 of the states. Now, what are the other 4? So there are 4 more states in this 3 by 3 space, and I'd like to just write down, another set of 4 more product states. But this is where the U comes in. U means uncompletable. That means this is a fundamental sort of fact about vector spaces, basically, but just happens, therefore, to be true for quantum states, that there are no more product states in the rest of the Hilbert space. So I get stuck. If I am enumerating states in this way, I have 5 product states, and I want more. There aren't any more. So this has stopped the making of any more product states. This I can prove, so I'll actually give you the proof. And it has to do with another sort of abstract diagram that we write for these states. And it has to do with the observation that I made here that, let's see, this was, now sorry, I'm going to call this psi 4. I decided on some numbering because of a picture I'm about to make. This is state 1, this is state 2, this is state 3, and this is state 5. Now notice that state 4, and this was state 5, in fact. This is psi 5. They are orthogonal, but, and this is a general thing about product states, that they are orthogonal either on the Alice side or the Bob side. They don't have to be orthogonal on both. Once they're orthogonal, they're orthogonal. I mean, they could be orthogonal both, but it's not necessary for their orthogonality. It's a little bit, there is a name which is called hyper-entanglement. This is slightly like the idea of hyper-entanglement. You could have kind of hyper-orthogonality, but there'd be sort of too much orthogonality. They don't have to be so orthogonal. Once they're orthogonal, they're orthogonal. And so these have the property of being orthogonal on the Alice side. And I'm going to make a little picture of that. So here are 1, 2, 3, 4, 5. So this is going to be the orthogonality diagram. And I need, well, either colors or I'll just do dashed lines and things like that. So I just established, or I just noticed, that 4 or 5 are orthogonal by virtue of being orthogonal on the Alice side. But they are not orthogonal on the Bob side. Now, the virtue of choosing the numbering that I just did is that all of these sort of neighbors in this hexagonal layout have that same property, which you could check by looking. Let's pick one at random. So 1 and 2 are orthogonal. Remember, this was Alice and Bob. And they're orthogonal. Here you take advantage of this sort of domino layout. They're orthogonal because they're disjoint on the Alice side. They're not orthogonal on the Bob side. But they're all mutually orthogonal. And in fact, the rest of them are Bob orthogonal. So I've drawn them all, but these dashed lines mean that 1 and 3, for example, are orthogonal because of their properties. Sorry, this was, I did screw this up. 1, 2, sorry, I did manage to screw this up because I started wrong, but I thought this would still be right. 2 and 3. Oh, no, okay, sorry. You got, I was saying the right idea, but my Blackboard dyslexia came in again. It's easier just to draw it again, making sure that I actually write the numbers that I have on my notes. 1, 2 is how I started, but I strangely put 3 here, and then 4, and then 5. So it's sort of a raster scan version, and then it's correct. As I was beginning to observe by saying, I will confirm it for you, and then it turned out to be wrong. Okay, I'm still going to go through the confirm it for you story. So this, forget this one. Okay, so, well, let's see. 1 and 2, this was Alice orthogonality. 1 and 2 are Alice orthogonal, yes. 2 and 4 are Alice orthogonal. That's because of this story. Yes, because of the minus being orthogonal to the plus. Let's take another one. 4 and 3 are orthogonal. Let me not take 4. Let's take 5 and 1. 5 and 1 are Bob orthogonal. So that was this picture. Okay, so anyway, there is such a diagram, this orthogonality diagram, and I even got it right the second time. Now here's the proof. Proof is very simple. I have a candidate state. Let's suppose I have a state and I say I've got it and it's a product state and it's a 6th state. Now it's got to be orthogonal to all 5 of these other states. And so I have to draw 5 lines This is only an example, but I have to draw 5 lines to each of these others to make a new graph. And I have to choose. They're either Alice orthogonal or Bob orthogonal. They could be both, but it turns out both makes it even worse. Makes it easier to prove. So let's suppose I choose that it's Alice orthogonal. This hypothetical entangled state is Alice orthogonal to 3 of these and Bob orthogonal to the other 2. And it doesn't matter which ones I attach these to, it turns out, but they have to be attached somewhere. But this is a problem, because remember, I'm in a 3-dimensional space, and I've got 3 vectors that I'm orthogonal to, and none of them coincide. That's the important thing, that there are 3 linearly independent. That's the other thing you have to check, that any 3 of these constitute linearly independent, not themselves orthogonal, but at least linearly independent vectors in 3 dimensions. There are already 3 vectors like this. They may have funny angles with respect to each other, but they do span the 3-dimensional space. Now I'm supposed to come in with a new vector, and they're supposed to be orthogonal to all 3 of those, and can't be done. You'd have to go into a 4th dimension. But by premise, by the construction of the game, we're only in 3 dimensions. So that's the end of the proof. Actually, it proves something far more. It proves that if you find a set of orthogonal states with this orthogonality diagram, that it's uncompletable without knowing anything about the specifics of those states. So it turned out the mathematicians found this pretty interesting. They had not heard of this kind of property before, and they proved other kind of interesting theorems about this, actually beyond our capability. The point of stopper is so in baseball there's pitchers in baseball, the guys who throw the ball, that often somewhere in the middle of a game a new pitcher is brought in, and they bring in specialists who are very good at stopping, the other team has been scoring, and this other one is, a great pitcher, and he comes in, he absolutely stops the scoring of any new points. So this state served that role in the, in the fourth inning, as we would say, of this 9-inning game. No, I'm sorry, it was in the 5th inning because it was the 5th state. Okay, so all right, now this was just, okay, that finally established what UPBs are. So they're mathematical objects that came about by just playing around. Now it turns out they have consequences for, let's say, quantum repeaters. So I'm going to jump in a rather big jump to something that sounds very experimental and has in fact something to do with the distillation of entanglement. So I will come back to that. I'll begin it. I'll do 5 more minutes, then we'll take our break. So just to get that set up a little bit. But I'm coming back in my mind to the question, why have I told you all this? Okay, nobody thought it was important enough to teach it in your master's lectures. And maybe they were right. I mean, I don't think this will be vital information for you. But it illustrates a few points that good theory comes from just playing around. I mean, BB84 was totally just playing around. And sometimes, well, the point of playing around is to find something beautiful. And in some mathematical sense, this was something beautiful, I thought. And then maybe it has something to do with experiment. And I'll give you that connection next. This connection is not as compelling, I will tell you immediately, as BB84, in the sense that it didn't lead to a whole new, methodology for quantum communication. It may be, well, I should maybe say it has a connection with BB84. In fact, it emerges from the same mindset that playing with these sort of orthogonality, or states that are conjugate in the sense of not orthogonal, but the 0, 1 versus plus minus, that is an attribute of BB84 that is in use in this little game. But it even, well, in the next section I'll tell you about states. It tells us about yet other quantum states that have very interesting entanglement properties and otherwise unanticipated before the introduction of this construction. So I'm going to just I'm going to write one more line of algebra. I guess I don't really have a place for it. I'll put it up here. So sorry, this is a bit randomly placed in this. So this is conceptually a new page. But I'll get a chance to clean up the board then on the break. So I have these 5 states. So somehow this has divided this 9-dimensional space into 5 and 4, and there's something special about those 2 spaces. So I'm going to make a projector. So recall, just as a general matter, if I have state psi I and I want to make a projector out of it, I write a symbol like that. That means, project on the ith state, project on this 1-dimensional subspace of this 9-dimensional space. But let me make a bigger projector out of it. Let's see, do I want to put the sum here? Yeah. Let's sum over all 5 of these states, including the stopper. So now I've made a projector onto this product space. Now I'm actually interested in the complementary space. So, the way to make a projector on a complementary space is to go 1 minus the projector. So here we write 1 minus this. So now that's a mathematical object, which is a projection operator that when applied to this space will project out everything except the things that are these 4 extra states that I'm trying to understand. The 4 states that are not product states but are still orthogonal to this state. And I'm going to do one further small step. If I write 1/4 here, then this is also a density operator. So this is itself a state. The point of 1/4 was to make this the trace of this 1. So it's a legitimate density operator. It has, it's also proportional to a projection operator. So its eigenvalues are 1/4 4 times, and then comma, 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 and then 5 zeros. So after the coffee break, we will explore the surprisingly interesting properties of this quantum state, and its, in particular, its entanglement properties. So now I'm pause that, and now the coffee and so forth should be waiting for us out in the corridor, and I see a nod. Any other logistics at the moment before we break? No. Okay. The bathrooms are in a very odd place, so if probably you haven't found them, but we can point them. They're near the front door, but that's otherwise they're unmarked.